Just quickly do the social media post and I'll be ready. Okay, so it is the 10 o'clock hour. So good afternoon or morning, depending on where you are. I want to thank everyone for coming to the first of a series of talks that we're doing. Hold on one second. So we're doing a series of talks on the application of synchrotron light sources to food, crop, soil, and plant and forestry sciences. There's a major international conference called PALSA that this year on those topics of the application of synchrotron light sources to agricultural systems. That conference will be at the Canadian Light Source in August. And running up to that conference, the African Light Source is going to have a number of talks and workshops for people who can't go there or have questions about how to get involved in the synchrotron applications to to agricultural sciences. So today's talk is by Dr. Scott Rosendahl, who is a beamline scientist at the Canadian Light Source. He is a physical analytic chemist by training, and his talk, he's responsible for the mid-infrared spectral microscopy beamline there. He'll explain what that is. And without further ado, we'll let him go ahead and get started. Go ahead, Scott.
Great. Thanks, Lawrence, and thanks for the invitation. And as suggested, good morning, good afternoon to wherever you are. It's morning here. And really, I want to start this talk with this idea of, so you want to do infrared spectroscopy to synchrotron. The reality is that synchrotrons are built for X-rays. It's a tunable X-ray source. And so why do you want to do infrared spectroscopy at a facility designed primarily for X-rays? And my hope through this talk is to kind of walk you through some of the notions of why it's good to have it there, and obviously some examples and to go from there. And as Lawrence mentioned, I'm Scott Rosendahl. I'm the senior scientist for the mid-infrared beamline here at the Canadian Light Source, and I've been doing infrared spectroscopy for probably 30 years now, which is kind of scary to think about, but it's kind of a fun idea to carry on. I've been working at CLS in some capacity since 2009, and I took on this position in 2014. And so, yeah, without further ado, this is a map of Canada, right? And this is where the Canadian Light Source is located. So we are basically right in the middle of Canada and right in the middle of the Canadian prairies. Because of that, we do a lot of agricultural-based research here at the Canadian Light Source, because we're surrounded by all kinds of grain crops, through livestock, through all kinds of crazy things. An interesting fact is that we will see temperatures from minus 40 degrees Celsius to positive 40 degrees Celsius throughout the course of our year. And in some cases, we will see a temperature swing of 60 degrees in a matter of 3 or 4 days. And so it's kind of an interesting spot that way, if you will. So the Canadian Light Source, what can I say? It is the third generation synchrotron facility located at the University of Saskatchewan in Saskatoon, Saskatchewan, Canada. It is Canada's only synchrotron. And as you can see, we are a double band achromat kind of setup where we have 12 cells. We have a beam energy of 2.9 GeV. We are a very small ring. You can see that we're only 170 meters in circumference, so we're pretty small ring that way. And we have a beam current around 220 milliamps in top up. So that's kind of where we're at in terms of our energy. We have over 22 beamlines at the Canadian Light Source, and we span, as you can see, a wide energy range from the infrared, far infrared kind of regions. See down here to the mid-infrared. So these are all sub-EV, all the way through to very, very hard, high energy X-rays down at our biomedical imaging therapy beamline, as well as our diffraction beamlines set up there. We do a variety of imaging, microscopy, spectroscopy. We even have some microfabrication facilities. And we focus in these four primary areas: health, environment, agriculture, and advanced materials. Some statistics about our facility, as you can see, based on the four kind of areas, we kind of are split pretty evenly amongst them all. I will say that materials is still the driving factor in terms of our synchrotron community, but we are seeing increasing growth in agriculture and environment, and health is slowly picking up steam as well. But I would say the fastest growing areas for us right now are in agriculture and environment. These are statistics from roughly a year ago. So we see about 400 publications a year. We have users from over 22 different countries. 1,300 of them are distinct. We have 260 staff located here, and we have collaborations across the world. So it makes it a very fun place to see. So you can see a picture of it here in the dark, all lit up, all pretty like. And this is a view inside during construction phases. This is way back in the early days of the CLS. And so I'm here to really talk about the mid-infrared spectrum microscopy beamline at the Canadian Lights. So I don't think a synchrotron talk is complete without first showing an electromagnetic spectrum. Again, just to kind of remind everyone, I'm pretty sure most of the audience is fully aware of all these things. But we have X-rays with wavelengths down to 2 nanometers. We go through the visible, where we're looking at 0.4 micron to 0.8 micron. And then we fall into this range of the infrared, where, you know, we can kind of start at about 1 micron and it kind of goes up to about 1 millimeter. Again, we see increasing wavelength that way, increasing energy and frequency going the other way. Nothing new there. This is a map of the Canadian light source, and we have, like I mentioned, hard X-ray beamlines. Energy is way down here to much lower energy infrared beamlines up here, and this is where I'm located. And for the astute among you, you will notice that my beamline is the only beamline that's going in the wrong direction. So all the other beamlines are coming off tangent very beautifully, whereas I come off and go backwards. So I don't know what that says about me, but what it does say about infrared light is that we could bend it much easier than we can X-rays. And so just a quick reminder, what we're really looking at in terms of the main interaction of our photon energies is we're looking at molecular vibrations. And so, you know, visible light, we're looking at those electronic excitations, the same too with the X-rays, but in the infrared, we're primarily looking at those molecular vibrations. The infrared region, like everything else, is split even further, again, into historical areas known as the near infrared to mid infrared to far infrared. And you can see these splits are primarily driven by technologies as well as physical phenomena. And so near infrared is primarily in the region where we have certain detectors that kind of reach certain areas as well as certain windows. And then you fall into the mid infrared, again, very similar. And then when you move past into the far infrared, again, much is there as well. In the mid infrared, we're primarily looking at the fundamental vibrational modes of molecules. But again, we're looking at the absorption of this infrared light with matter. And so with infrared, we could get a lot of information about the identifying materials as well as the structure of compounds and molecules. And further to that, we can get quantitative information. It's just a matter of setting up your experiment correctly. And what I really want to highlight is this need of, you know, when we're trying to understand materials, the what and the where is very important. And this is where the spectral microscopy comes in, but also too when can also help. And so that's the time resolved component of all this. And infrared is just another tool in the chest of tools when it comes to exploring materials and samples. And And really, we're seeing a lot of multimodal kind of activities, making it very, very useful in terms of expanding the information of what's happening. And that's where infrared kind of comes into play. And I'll talk more about that as we kind of go forward here. So again, we're a vibrational spectroscopy. So we're looking at the periodic motion of basically two atoms in a kind of a simplistic case. You can imagine Hooke's law, basically where we have basically two masses connected by a spring of stiffness. Okay, and those correspond to the vibrational kind of energies that we see in a typical plot like that you would see like that. What's very interesting to note is that there must be a change in dipole moment for a vibration of molecule to absorb infrared radiation. And this is different to Raman spectroscopy, where you need a change in the bond. It needs to see a change in polarization. Here, it's entirely due to a change in dipole moment. Kind of also interesting to note is that when you start looking at molar absorptivities, so if you consider Beer's law, again, that epsilon variable describing molar absorptivities, you see that in typical UV vis kind of spectroscopies, you're looking at, 10 to the 5 to 10 to the 6 kind of numbers, whereas the infrared, they're much smaller, right? So again, you're looking at very kind of much smaller molar absorptivities, but it's still very selective, which is very useful. These are some examples of what a fundamental vibrational mode for something like water might look like. So again, this is typically where if I was in a class, I would be doing a dance where I use my arms to demonstrate the motion of these molecules to try and highlight the different modes. But you try to see here that we have kind of a symmetric stretch with the hydrogen molecule atoms above the oxygen molecule in the middle. And you can see that they occur at various energies. Again, an asymmetric stretch, slightly shifted, as well as a bending mode, where we see, again, a much lower energy is required in the bending mode. And because of this, these various modes allow us to learn information about these molecules and the state that they're in and how they're connected. That's not to say that every two atoms connected together or molecule is going to demonstrate an IR spectrum. And I kind of mentioned that briefly. Whereas if we don't have that change in dipole moment, as you can see here with a molecule like CO2, you see that this molecule this particular stretch is relatively inactive. So this particular stretch of CO2, we won't be able to see. However, the asymmetric stretch is active. And so it kind of demonstrates that even though that some aren't, some will be, and we could use those to highlight what's there. And I really like to highlight these two particular molecules here, water and CO2. When it comes to interferences in infrared spectroscopy, these are probably the largest two that you will see. So water being a very good solvent, being everywhere. It has a lot of vibrational modes, particularly in the low vibrational spectra, which I'll show next. And so it can become an interference in a lot of spectra that you look at, whereas CO2 is present everywhere in the air that we breathe, et cetera, et cetera. And so when it comes to trying to take measurements, we try to work in very purged environments of both gaseous water and gaseous CO2. And you can see here, this is a spectrum of water in the vapor stage versus the liquid state. Okay, and you can see that we see fundamental shift in location of where these vibrations are occurring, as well as much more broadening of the peaks or the band in terms of the vibration of water. And if you're trying to pull some information out in these particular regions, you would see that it's very difficult to do because you're going to have lots of overlapping areas in these spectrum. But what is a very unique and fun thing about infrared spectroscopy is that it's an old science, I would say. I mean, people have been exploring infrared for decades. And as a result, there is huge books of tables of various kind of chemical bond motifs that you're looking at, the compounds that exist in, where these particularly bends and frequencies show up, and their intensities. So it gives you an idea of what their molar absorptivity is or their molar cross-section are for those particular kind of settings, and where you might be able to find them, which is also very, very useful tool to kind of explore infrared spectroscopy with. However, that being said, this is a spectrum that I pretty much see every day and have seen every day for the last 20 years. And this is what a typical bio life plant food infrared spectrum will look like. And what I mean by that is it's any sort of material that has lipids, proteins, DNA, and carbohydrates present is going to basically look like this. And so we have regions of the infrared spectra here that we can, associate primarily with lipids, with protein. Okay, so this particular band here, these two bands, amide 1 and amide 2, are very good reporter bands. If you look at the phosphate kind of modes here, from nucleic acids and carbohydrates, again, down here at about 1300. These all make up what we typically see for all bioplant kind of base spectra. And it's very interesting that we could start to explore these regions even further. And so this is just a zoom in of that amide 1 band, which is a very important band when it comes to analysis in the bio life science spectrum, if you will. And you could see that within that band, we could break down the various kind of structures of protein. So we're now looking at that secondary structure of proteins. So we could look at the beta sheet formation, the alpha helix formation, how much are unordered or turns basically in those structures. And this again becomes that very, interesting kind of idea of when you start to analyze how certain diseases kind of can affect these regions. And, a common example of that would be something like Alzheimer's, where we see, breakdown of the secondary structure of these proteins that form these plaques within the brain. And those changes are very sensitive in the IR spectral region here. And so we're able to analyze and look at that. And so it's very useful. What's also useful is that we could do imaging with spectroscopy. And this is, again, kind of starting to build the case for why we want to do infrared at synchrotrons. And again, I just want to remind people that we can do this hyperspectral imaging, again, infrared, where we have a sample on some two-dimensional plane, X, Y. And as we go into the page here, we see we have a full-on energy spectrum, and we can have different absorptions based on that, giving us that spectral microscopy of our sample. And so we could pull out different regions, again, look at the spectrum at those different regions and compare them. And we're able to produce those chemical maps of those regions. So again, highlighting, differences in this region here to differences in this region here. Again, this allows us a tool that we're able to kind of explore these kinds of spectra with. And really, at this point, I just kind of want to make a kind of a shameless plug here, if you will. A data analysis package that we use to do all of our processing of our data here at Canadian Light Source in the infrared is using Quasar. And it's an open source data analysis tool that has been developed by many infrared synchrotron kind of researchers around the world. And it allows us to be able to produce some of these images that I'm going to show you coming up, as well as allow us to do the kind of analysis that we need to do. And so we're able to do advanced clustering techniques, k-means, hierarchical clusteral kind of stuff, as well as PCA analysis. But I just want to point out that this is what we're using to do the images that you'll see next. And so with that, this is an example of a canola seed. Again, canola is a very important crop to Canada, in particular to Saskatchewan. And it's a small seed, a small round seed. And we're able to image this. You can see the image bar here. So this is about 500 microns across. And using an RGB map, we're able to overlay the various components within this seed. So you can see that the carbohydrates we have kind of in blue, the lipids are in reds, the protein here is in green, and then as you can see, we could overlay this map. We get a sense of where these components are within the cell and how they might change with various perturbations. We could then further extrapolate details out from this. Again, you can see this is kind of a section edge here. This is kind of up in this neck of the woods here of that same seed that you see. We could do multivariate analysis, in this case, thinking about doing PCA, k-means clustering, and could start to classify those particular spectra with what you're looking at. In this case, this is k-means, and you could definitely see the various components being pulled out, as well as what those spectra look like. So this is a very powerful tool that allows us to combine the spatial information as well as the spectroscopy information, which is where the spectral microscopy aspect comes in. And so it's a very powerful and useful tool. And so, again, why do we need a synchrotron to do this? What is so valuable about a synchrotron when it comes to doing this IR kind of spectral microscopy? And it really comes down to this idea. And so a traditional infrared spectrometer that you might find in a lab uses basically this glow bar, which you can imagine is just being a black body. It's a ceramic that's current passes through and it heats up. And so we're using this heat to kind of produce the IR photons, the required energy for what we need. We in synchrotron land like to talk about brightness, okay? And that's the units over here for brightness that I'm using. And basically what it means is that we're looking at the number of photons per second, so kind of a flux, but it's within a striation kind of area. And so you see that component here. And so with the glow bar, conventional glow bar source, we get a lot of photons, which is great. And you'll notice that the photons are going around or being emitted in all directions. When we switch to using a synchrotron, you'll see that photons are very, very, very much focused going in one line, okay, very like a laser, if you will. And we see an increase in brightness by 3 orders of magnitude. Okay, so this order of brightness increase is what starts to become very important for the synchrotron. And I'd like to point out that if you were to just use flux as your kind of notion for energy, you'll notice that the glow bar actually produces more photons in more directions and has a higher flux overall compared to the synchrotron. But it is this brightness factor, this kind of focus beam of synchrotron light that makes it valuable. Again, similar to a laser. Most IR beamlines around the world are basically utilizing dipole magnets or bend magnets within storage ring structures. It's no different here. And basically, as synchrotron lights, as the electron beam passes through the dipole magnet, it produces a fan of infrared light. This infrared light has structure based on the wavelength of light. And so the further you move away from that center plane of fan of IR photons and photons being produced in the bend magnet, you get different basically distribution of the light. And so you can see as you go further and further away, you have a larger contribution to the higher or the lower energy, longer wavelength light, than you do closer to the overall plane, if you will, of the synchrotron light. So how does this all manifest in terms of uh, spectral microscopy? And this is probably my favorite slide. It's very kind of cartoony, but kind of good how to illustrate this. And we set up a microscope where we vary the size of the aperture. So again, the aperture of light, looking at the sample, and then the relative brightness. Again, this is just a kind of an idea of where things are at. We're comparing the glow bar and the synchrotron. So at very small aperture sizes, again, this is now when you start to think about, okay, so infrared light, mid-infrared light. We were mentioning earlier that the wavelengths of that light are anywhere between 1 micron and 25 microns, or 2.5 microns to 25 microns. And so you're starting to get a sense of, okay, the aperture size is now approaching the size of the wavelength of light that we're looking at. And this is where the glow bar starts to fall off. So that your conventional source just starts to fall off in terms of being able to take those measurements down at those smaller aperture sizes. Whereas the synchrotron, again, due to its large brightness, is very good. And so, when we talk about, 10 micron kind of aperture, you'll see that the synchrotron light sources totally outperforms a glow bar source, which is why we start to need this at the synchrotron. It's interesting to also notice that as we increase the light source, the aperture size further, the glow bar will overtake the synchrotron in terms of brightness, again, just due to the sheer number of photons coming off the glow bar compared to the synchrotron. And so when it comes to doing bulk spectroscopy, bulk materials, this is where synchrotron isn't as advantageous, because we're not overly confined by those size constraints. So this is just an example of what if we look at kind of fraction limited light. So again, half the wavelength of light using the definition of the fraction limited there. So with 6 by 6 micron aperture, this is a full infrared spectra, and you'll see that we have the glow bar. This was 1,000 scans, and it took 500 seconds to measure. This is the same aperture size, now utilizing a synchrotron source, and you'll see that within 32 scans, in only 16 seconds, we have a huge increase in the signal to noise. And this is just like trying to do imaging on, let's say, the Mona Lisa here with a glow bar, being a very small aperture, not getting all the light through, to what the synchrotron provides, and that is basically giving us a much more focused image of what's there. It is at this point that I really, really want to highlight and make sure and make it clear that the synchrotron radiation offers better signal to noise by lowering the noise. Okay? It does not enhance the signal. Okay? So that is something to make sure that you're aware of. Basically, what I'm saying is that it can't create material. Okay? So it can only measure what is there. So if you have a small concentration of material, synchrotron is only going to help by lowering the noise floor. In terms of the measurement, it's not going to be able to increase the signal strength of the measurement that you make. Hopefully that makes sense. Another way to think about this is, again, if we look at the spatial resolution, we're going to look at 2.5 micron light. So this is basically doing some imaging where we're looking at this is a 1715 inverse centimeter kind of spectral range. So as we decrease the energy, we're increasing the wavelength, you'll see that we are losing the resolvability of the features that we're trying to measure. And again, this is just due to the below equation here. And you'll see that at 2000 inverse centimeters, Okay, that's basically where the glow bar starts to fail, right? Or really demonstrates failure there, whereas the synchrotron could still make out the information there. Hmm. So, how do I do all this? So, running a beamline has a lot of very talented people involved, and I basically try to combine all their strengths to make everything work and one run as it should. Uh, and these are some people that were very instrumental in the last few years. And so Professor Ian Burgess is what we refer to here as our beam team leader. He's a external specialist in infrared spectroscopy. And so we lean on expert advice from outside to help make things run. Stuart Reed was the associate at the Mid-Infrared Beamline. He recently moved to a data scientist position here at the Canadian Light Source, but he was very instrumental in getting a lot of the beamline work done and running. I have a lot of support in various aspects in running science programs. And so Amanda Quirk is the scientist at the Beamline that specializes really in the bio-life science kind of sciences. And Kai too. And Grace just recently started at the Beamline. Kai is the scientist responsible primarily for the agricultural, food, soil kind of projects here at the Beamline. And much of the work discussing those is work done by Kai. So I want to make sure I give a acknowledgement to Kai right now that pretty much all of the plant-based and food-based projects are work done by Kai. Grace just started when Stuart moved from the Beamline. Grace is the associate scientist at the Beamline. So more specifics about the Beamline for those that are interested. So photon energy, as you can see, we kind of dip into the near infrared a little bit, and we go out into the just touching the far infrared. We run into limitations due to the optics in our beamline, that being beam splitter as well as various windows in place. Photon flux as a result of the dipole magnet that we have. And we have a variety of instruments. So I have a Brooker Vertex 70 spectrometer with a Hyperion microscope. It comes with focal plane array, 64 pixels. This is an online instrument. Agilent Carry spectrometer and microscope. This is an offline instrument, much larger pixel array. Time resolved instrument. We built a horizontal end station and recently added a QCL laser light source. This is a image from our M2 mirror. You could see the bands of light with where the X-rays would come through. Otherwise, the M2 mirror. This is a optical layout of the beamline to again give you a sense of how we're laid out. So the electron beam passes through here. We have a split M1 mirror, and that basically allows X-ray light to pass through and reflects up the IR invisible light into our M2 mirror setup here. M2 goes through our focus and our diamond window that separates ultra high vacuum of the storage ring from rough vacuum of the beamline through a variety of optics. We bring the beamline or bring the light down to an active optics kind of setup here on the optical table, where we're able to capture this as a kind of an image profile of what the beam looks like at the microscope plane of the Brooker Hyperion 3000. These are images of the instruments. So again, this is the Brooker spectrometer setup. We do spectral microscopy using ATR chemical mapping. I'll talk about that briefly here. Fraction limited full field imaging. And another thing we like to do is polarization and how to image with polarization. This is our completely offline Agilent setup that is good for measuring biological tissues. One of the interesting features about focal plane arrays and synchrotron light is that synchrotron light is very small and doesn't fill FPA. And so with light, and so a glow bar source actually puts more light, as I mentioned earlier, just due to the flux in all directions onto the FPA compared to a synchrotron. So this is why this instrument is better utilized offline, where we just use a glow bar source to image with the FPA. One of the most recent updates to the beamline is we built a horizontal ATR microscope, horizontal attenuated total reflection microscope. This I'll talk more about in the next few slides, but just wanted to kind of introduce it there. We have a time resolved spectrometer that uses a dual beam heterodyned kind of ballast detection to look at very fast spectral changes in the infrared. There's a very small frequency comb band, as you can see, 1620 to 1680. This particular frequency range was selected around the amide 1, where you can see a lot of potential protein changes as a result of whatever kind of perturbation you apply to them. And we just recently added a QCL-based light source to the beamline. Bandwidth here is in the fingerprint region, so from about 1800 inverse centimeters down to 800 inverse centimeters. Again, it just provides us with a nice high brightness source that we could use offline when the synchrotron light is not in use. And so one of the, I guess, the interesting techniques to use with infrared spectroscopy is the attenuated total reflection. And it is the best tool to use for difficult samples. And when it comes to doing food, plants, these kinds of things, this is where techniques using ATR become very advantageous. And so a lot of the development and a lot of the work done at the beamline that stands us out from other beamlines around the world is in using ATR in terms of the various in situ kind of techniques that we use. And so just to kind of remind everyone, when IR light bounces off an interface between two different materials with different indexes of refraction, produce an evanescent wave that basically penetrates beyond the surface. This wave can then interact with material that's sitting on top of it, and it's kind of limited to roughly 1 micron depth of integration of the sample that's sitting on top of the crystal. It's important for this technique to work that you have good quality of contact with the sample and the crystal material that you're looking at. It changed the penetration depth by altering the angle of incidence. And again, this all follows this wonderful equation here if you're really, really interested. But this is really the lead-in into this horizontal ATR microscope that we built at the beamline. And what it is it's a basically it's a bottom-up illumination freshman geometry. So this allows us to put materials peanut butter side down, if you will. And so this is very useful for things where gravity becomes your friend. And so when you start thinking about building electrochemical cells or microfluidic devices on top of this ATR crystal, you basically don't have to worry about penetrating light from above, which is what makes this particular platform very, very flexible. It's integrated to both synchrotron and glow bar, and most recently our QCL source, so it takes advantage of all 3 sources that we have at the beamline. We could do single point spectroscopy with it or spectrum microscopy. Our stage is movable and can move around. We could also use a ray detector here to be able to do chemical imaging with it. And really, we brought this on in 2018. COVID kind of slowed its progress, but we really picked up with it most recently. And so this is an example, I guess, of some of the wide imaging characteristics and capabilities of this. So you'll see that we have our stage platform is here. Again, this is the crystal that you can see here. It's just upside down. And on this crystal, we have the IR light coming in and out. And on top, we have a microfluidic device. So we have two channels. Two different fluids can be pumped through there. And then the fluids follow this path. As you can see, this is the top-down view. And you can see overlaid is the IR images that we're able to produce using this microscope. And what is really, really fantastic about this is that you'll see that each of these is 500 microns, kind of by 500 microns, the channel width. But we have an imaging area of close to 8 millimeters in this direction here. And so it's very large area, allows us to look at things like live cells, cathode materials, as well as microfluidics. And so it's a very powerful platform. Some of the example applications that we've seen using this, again, I know we're talking about food and everything like that, and I will get to this. I apologize, I'm a physical analytical guy, and so a lot of the instrumentation is built with that in mind and then utilized after the fact. And so this is kind of the lead into those kind of discussions. And so in this case, we have a micro machine piece of silicon. As you can see, it's got these various grooves along the bottom. We bring our IR light in and we do ATR on the sample above. We're able to look at co-flow of basically water and D2O through these kinds of things as well. In this case, this is just an example of the spectroscopy of water. You could see that this is SU weight or a polymer material. And as we go through the channel, we see the definite switch over to the water. You can see that full width half max is around 70 microns. So it's pretty good, pretty exciting there. This is imaging using this kind of technique, which is kind of fun in itself. So we image this area of this device here. So again, it's very similar to the previous one that's micro-machined silicon. And we flow one with water, one from deuterated water or D2O, and they co-flow here and they form a laminar flow in this particular regime. And we're able to image that using our FPA detector on this device, which is pretty cool. And then you can map that out so you can see where the two channels, H2O, D2O, and in between we have the mixing or the ionic exchange of deuterium with hydrogen and water, which we call this HOD, which is pretty cool. Now, I've talked a lot about the spectral microscopy. I will say that in the infrared world of synchrotron-based sciences and infrared microscopy in general, imaging beyond the diffraction limit, so imaging into the nanometer space or sub-micron space, is probably the fastest growing infrared community. I would like to say here at Canadian Light Source that we're in that game, but right now we're not. And so we're trying to get access into this through different instrumentation. But I will say that most infrared synchrotron facilities around the world are utilizing nano infrared to image their samples, and so you're able to go beyond the diffraction limit. So now this puts you on the same fraction space as something like STXM, for instance, or scanning transmission X-ray microscopy, where you're effectively on that 40 nanometer range. And so a few years ago, I was able to get a demo unit of this NeoSpec instrument operating at the beamline. Very simple to set up, which was great. And we were able to, like I said, reach about a 40 nanometer kind of spatial resolution of this guy. And so for me at Canadian Light Source, this is the area I am trying to get into and actively seeking collaborators as well as grants and funds to try to move into this range. These instruments are very expensive. They're, for me, on the order of 1.5 to $2 million each. And so it has been a little difficult to break into, but I'm not alone in Canada. There's quite a few people trying to get into this, but this is definitely the fastest growing area and something to keep interest and keep an eye out for in the future. And so just going to shift gears now into some example applications. Again, trying to get to this idea of plant food and everything like that. So I got about 10 minutes left. And so I'll kind of go fast through some of these and then slow down into the food-based ones. So for those of you that are interested, this gentleman here is Peter Griffiths. He wrote the book on IR spectroscopy. So for those of you that know, that's him. It's kind of very cool. We had a conference with him a few years ago. But similar to what you saw earlier, basically the project at the CLS beamline, mid-IR beamline, basically follows the same thing. So I have projects all over all the map. We'll be studying things from microplastics, which is a very hot topic, through what I'm calling fake meats and cheeses, as well as chocolates. And so I sometimes joke that when we're doing these measurements on the microscope, I have the world's smallest charcuterie board, which is kind of a fun thing to say. Cultural art heritage science. So we have done some collaborative work with conservation institutes here in Canada, as well as the National Art Gallery here in Canada, to look at some of their artworks and to study them further, as well as the biomedical side of things. So looking at stroke, MS, which is both huge health problems here in Canada, and particularly in Saskatchewan. And so kind of what we do. I have a list of publications, more recent ones, if you're interested to take a look there. Touching briefly on the cultural and heritage science. So within Canada, we have a movement of arts that came out of these 7 artists, and we call it the Group of 7. One of those particular artists is Lauren Harris, and an interesting issue with his paintings is they're chipping out, and so we're seeing the formation of these metal carboxylic kind of salts, and they chip out, as you can see here. When we do imaging of these things, this is a chip actually that fell out of that blue painting there. And so you see the Prussian blue is that blue color. These are the bands associated with the Prussian blue. Oh, no, sorry. The bands would be somewhere in here. We don't see them in this particular picture here. But you can see that with the microscopy side of it, spectral microscopy, we're able to image and determine where these various things are forming and showing. And so can see that we have the zinc carboxylates, which is the primary culprit in terms of the chipping out as these forms these metallosalts. My physical analytical side was primarily looking at incorporating spectroelectrochemistry, so electrochemistry in situ. And so I built thin cell kind of device to measure electrochemical reactions, time resolved within IR. And so I put one of these things under a microscope. I was looking simply at ferrocyanide chemistry, so iron 3, iron 2 chemistry. And by changing the potential from one side to the other, I'm able to track the electrochemistry, or basically the rate of that electrochemistry in time in the infrared, using Beer's law, we're able to then produce a plot where we can look at the IR response, which is the purple here. The black is what we simulated in the IR response. The red is the electrochemical response. The difference between the two is the result of the fact that electrochemistry also happens on the edges, and you're constantly producing material, whereas in this thin cell geometry with the infrared, you can imagine that we're probing light from above, and eventually the space and the area and the volume that is being probed by this IR light gets saturated. And that is what we see here. So we see a saturation of the IR signal as a result of the thin layer geometry, which is why our electrochemical signal is different. But what is very interesting is that we're able to see a limit of detection of 36 femtomoles, which is pretty cool. This was further improved by moving to ATR and using CRAS. So we used patterned gold kind of substrate in order to be able to increase the signal or use surface enhanced techniques. And you can see, it might be difficult to see, but we got down to 2.5 femtomoles of material, which is pretty cool. We could do IR spectroscopy in extreme environments. So again, diamond anvil cell, put material in there. We squash the two diamonds together. With this, we could see phase changes as well as molecular kind of changes as a result of the molecules being pushed further and further together. And this shows up in the IR spectra here, which is very cool to see. Polarization is another thing that we play with. So by using linear polarized light, you can probe different bands within these chemical structures, which is kind of cool. So using different polarizations, you can highlight different regions of these photonic materials. This allows you to potentially drive different reactions as a result of these plasmons and surface plasmons there. Extending this out further into vibrational circular dichroism. Again, this is where we could start to get a lot more information down in the alpha helix and beta sheet, because again, one is more susceptible to the alpha helix kind of structure. And this is really where synchrotron light and the QCL laser really come into play, because these polarization techniques are very photon-starved experiments. And so you need a lot of photons in order to be able to do these, because the absorption cross-section for these various polarizations is on the order of 10 to the minus 3 to 10 to the minus 6 for VCD. So it really takes a lot of IR photons to do these. And this is, again, where synchrotron IR based spectrum microscopy and using QCLs is very, very important. We look at stroke. So again, this is a mouse. You can see we have stained versus stained. We could look at the various contributors in those particular things. So again, giving us that spatial kind of information about what's happening. And temporally, you could do this by starting stroke events in these various mice at different times. So we could see where protein structures are primarily predominant versus lipids and aggregated protein as a result of, you could see where the stroke events occurred in this poor mouse's brain. You could combine a whole bunch of these thin slabs into basically a reconstruction, if you will. So this is a mouse brain, and these are various sections going through the mouse brain. So in total, there was 112 sections that kind of give you a view of the different components within the mouse brain. And so this gives us kind of a normalized atlas that we could see to further studies of these guys. Studied biomaterials. So again, this is kind of a sample matrix that would be, it finds its kind of structure in dentistry. And so the idea of using fillers and resin to produce fillings in teeth and the degree of conversion when you know the dentist hits your filling with that UV light, how much filler can be put into these things while maintaining the strength of these particular composite materials, and what the structure is around them. And so we could use IR spectroscopy to look at the degree of conversion at a distance from these guys, which is very exciting. So now kind of switching into some more of the food kind of soil plant-based things. One of the things that have looked at is the application of what salt does to and how salt is affecting the growth of these particular plants in alfalfa. So you see that we know that saltification is a problem in terms of the soils around the world, and we wanted to explore what that looks like, and we definitely see structural changes as a result of changing the salt concentrations in these plants, and what that looks like as the plants are growing. And so you can see the various cross sections that are used to see differences in lipid structure as well as protein structure of these stress plants. An interesting area that is also being looked at here is looking at chocolate. Actually, this is kind of looking at how tempering of chocolate changes the crystal structure as well as taste and feel of chocolate. And in this case, we use model systems like DMPC, which is this guy down here. And as we slowly, or as the researchers slowly change the concentrations of DPMs with this triglyceride component here, you can see we have an upsetting, if you will, of the structure of these kind of materials, right? And so we see the collapse of these order MPC micelles, and things like this, additives in chocolates, and how this affects the tempering and taste feel of chocolate is something that we're able to measure and use in the infrared. Wheat germination. So again, using this RGB color maps where we have lipid, protein, and carbohydrates in their representative colors. We can see that as the wheat seed germinates, so at time 0 through time 24 hours, we see quite a depletion of basically protein as a result of the endosperm growing out. And so we could spatially see this, which is absolutely fantastic. In the time series between these things, we could watch and monitor the growth of all these things. And so now you can imagine we have a kind of a base set that we can now utilize to explore what happens in different drought conditions, or fungal pest kind of conditions, on how that affects the germination of these guys here. And these are all done in the infrared, which is very fun. Another interesting area is pollen formation. And so pollen, very important to understand. And with IR spectroscopy, the wavelength of light is very good at analyzing pollen grains and pollen kind of size. And the development of pollen, in this case, in a rhopodiasis flowers, when analyzed using PCA, is very good at basically isolating out the transformation of pollen as it grows. And so it is even better than using visible light microscopy to understand the stage at which the pollen formation is at. And so with infrared, we're able to better understand or look at the change in pollen again, in these various kind of components, which is very exciting. And with that, this is just again a kind of a tip of the iceberg on all the great things that is going to be presented at PALSA this year in Saskatoon. There's a QR code here to gain access to the basically the PALSA conference site. It's from August 20th to 22nd here in Saskatoon. We'd love to have as many people here in person as possible. We know that is not necessarily always easy and available for some people, and so we do have a hybrid mode as well if you're interested. And so please, I encourage you to check out the website for the PALSA conference. And finally, I want to again thank the people involved in making this possible. Again, Stuart Reed was hugely involved at the start of everything. Toby Bond helped me do good reconstructions of the mouse brain you saw at Kayang 2, basically all the plant-based stuff you saw. My manager, Ian Burgess, beam team leader, as well as other researchers around the facility. So I like to say at this slide, I'm on here twice. You might be able to see me here. That's one time. The second time, I'm actually that person standing right there in front of the CLS. And so with that, I want to thank you for your attention. I will leave it up to Lawrence in terms of facilitating questions if we have any. And thank you again for your attention and this opportunity to talk about why you might want to do infrared spectroscopy at a synchrotron or an X-ray based source. So thank you very much.
Thank you. Let's just give a round of applause quickly to the speaker. And if there's any questions, just raise your hand, unmute yourself, and ask away. Because there's so many people here, I probably won't see everything. Is there any questions for the speaker? You can also put your question in the chat if you want. Let's see, are there questions in the chat? Don't see any. I see some. Hold on, this one just came in, I think. One question is from Gabrielle. The germination seeds, how were the samples prepared?
So any of those kind of projects, the samples were grown in growth chambers, and at the various stages were pulled out of the growth chamber, and from that, the seed germination was flash frozen in liquid nitrogen and was cryo-sectioned into sections that are on the order of 7 to 10 microns thick, mounted on calcium fluoride slides, and then from there were analyzed in the infrared. Sectioning seeds is very difficult. That outer coat is stronger than you like to believe, and could result in a lot of smearing when you do the cryo-sectioning, and so it takes a few attempts to do it. But yeah, that's my recollection of how they were done.
Why calcium fluoride? Is that IR dead?
Yeah, so calcium fluoride is a very good kind of it cuts off around 900 inverse centimeters, so it doesn't cover the full IR spectral range, but it covers the spectral range of our FPA detectors. So many of the windows on our FPA detectors cut off there anyways, which is good. Plus it's clear. And so many other IR substrates aren't clear. And so that makes it a useful substrate for that.
There's another question from Mohammed. Do you want to ask it, or do you want me to read your question? Well, I'll just read the question for time, in the sake of time. What is your beam time application cycles? So when can you apply for beam time?
So in typical years, this is an atypical year for us, but in typical years, we have 2 applications or calls for proposal. They're about 6 months apart. So we run in 2 cycles, a January to June cycle and a July to December cycle. And so you can imagine that If you wanted time in January, you would be applying for time in July, August of the previous year, of the previous cycle. It goes through a peer review process, and those proposals that best align with our research goals are chosen to do the experiments at the beamline. I operate basically all the time because I could use offline sources, and so some projects utilize offline sources. But for synchrotron times, yeah, I'm limited to when the synchrotron's there. But yeah, we basically are all around. So
Okay. Fatima or Fatima, your hand is up. You're muted. Go ahead.
Hi, can you hear me? Can you hear me?
Yes, go ahead.
Okay, thank you for the interesting lecture. That you mentioned the output of the synchrotron light for your beamline is polarized.
So it's slightly polarized, but the reality is that at the microscope we're really seeing that polarization is lost. And so the combination of the two bands overlap, and those two stripes, and as a result we see basically half and half S&P polarized light at the microscope plane, which is useful for us. And so we throw a polarization modulation setup in front of that, and we're able to isolate S&P polarizations or perpendicular parallel light to the microscope or the imaging surface, and we could do imaging that way.
Thank you. Because I'm not an expert in IR spectroscopy, I'm doing Raman spectroscopy, but it
Right.
was always a question for me that does also IR is sensitive to the crystal polarization when we do imaging or not?
Yeah, you can imagine that when we're looking at the change in dipole of the particular vibrational band, it has to be in line with the light. So if your vibration is this way, your IR light also needs to be in that same plane in order to excite that particular mode. And so that makes it very sensitive to the polarization of light.
Thank you.
Yep.
And one more question, if it is possible to ask.
Go ahead.
For the brightness, because your most, so let's say you made it bold that the main advantage of the synchrotron is the brightness. But for the measurement, you don't need to reduce the power on your sample, especially when you are doing biological imaging.
No, we're still really not at the stage of heating the sample up at these kind of energies. When you move to the QCL based laser, for instance, it can cook your sample for sure. We have to decrease the power for sure on it, as well as these infrared free electron lasers. There's too much power there on those. But for the synchrotron, the amount of power that it puts into the sample is very small, and it matches very well to the energy dynamic range of the MCT detectors that are used.
Thank you so much.
Okay. I have a question here from Javed, and his question is, what role the synchrotron can play in determining food quality? So I imagine there's some molecules that sort of indicate some sort of quality, maybe.
Yeah, and so I mean, when you start thinking about quality is a very quantitative kind of attribute to look at, and so some projects we look at. I'm gonna take a different approach to what is probably meant by quality here, but when designing synthetic or kind of simulated meat products, for instance, determining how much protein and how much fat to put into these particular materials and how they segregate in and out, because it's actually a very cool surface chemistry experiment, right? Because we have the interplay between the fats and water effectively, and so you end up seeing some very interesting surface chemistries that take place at these interfaces, and so relating the quality of food, so basically the quality of what the simulated meat tastes like to what real meat tastes like, can be looked at and changed and modified based on what the structure we're seeing in the infrared light is. Another way, I'm sure, is maybe more the intention of the question is that, yeah, you could utilize the degradation of food. So if you're looking at the fruit or something like that is sitting on the shelf for an extended period of time, you could see it change with time as it becomes oxidized, for instance. And same too in meat and proteins, right? You could see that change in oxidation of meat going through there. So you can use it. And near-infrared spectroscopy is used quite a bit in determining food quality that way. And mid-IR not so much, just due to technological reasons. It's cheaper to set up a near-infrared system than a mid-infrared system. But as those barriers are coming down, more and more mid-IR stuff is coming into play. I hope that kind of answers the question.
Javed, if you're still here, you can follow up if you want. There's so many pages of participants. I don't see where he. Javed, okay, I see you. You're muted if you want to follow up. Okay, I'll move on to the next question.
Sure.
Excuse me. I have a question.
Right. So
Will be modified.
go ahead. Is it
Antonella.
Antonella? Yes.
Antonella,
Go
yes.
ahead.
I would like to ask Dr. Rosendahl if he has an experience in the study of organic material in corals using infrared radiation.
In corals, so calcium carbonates are magnesium carbonates, kind of that dolomite kind of stuff. There are bands that you can look at down there, and it is kind of they are weaker. And again, just comes down to we have a cutoff of our detector down there, but we can see them and can look at those. I personally have not studied a whole lot of coral, for instance, but I have looked at some rocks and rock formations, as well as incorporating these calcium carbonates, for instance, into cement and looking at cement. Yeah, that is kind of an area that could be used to look at those kind of materials for sure.
Yes, because I read a paper where they said that they can distinguish between natural corals and artificial ones, looking at these black protein polymers. But
yeah.
Could you explain what are these black?
I would have to read the paper for sure to understand what that is, but you can imagine that it's the excretion of these coral-based lifes that also contain protein compounds in there, compared to what you would see in artificially made things, right?
Mm-hmm. Okay, thanks.
Okay. So going back to the whole quality thing, I think there's a question here about water stress in crops. And
okay, yeah.
I'm taking that to mean
drought tolerance.
Yeah, drought tolerance. How much water is in? So you look at water bands being there or not being there, right?
Typically, we're not looking at the water bands. We look at the result of that. So once the sample is pulled out, it is basically freeze dried and looked at that way. And so looking at these things in situ is very difficult, because the plant material is thick compared to what we're able to measure in the infrared light. And so water being a strong absorber, you can't have a sample that is 20 to 30 microns thick and get light through it. It is very, very difficult. So we have to, unfortunately, kind of work in an ex situ kind of experimental environment, where we take the sample that we're looking at that is grown in the various conditions of moisture, humidity, for instance, and then analyze it ex situ.
Okay. And I think one last question is from Heba. Do you want me to read it, or you want to go ahead and ask your question if you're still here?
I can read it.
Okay, go ahead. Yep.
I want to ask about how much time it take to conduct a research in agricultural field related to plants microbial interaction. So we can, for example, track the element, the chemical material that is communicated between plant and microbes, the beneficial microbe. And also, at what stage it is good to take samples for such study?
Right. Well, I mean, yeah, when it comes to how long it takes, the measurement time itself is on the order of minutes. So it doesn't take long to actually take the IR spectrum. What actually takes the longest time is growing the plants. And as you're probably aware, you're looking at, run times and lead times that could be in the order of, days if you're looking at germination to weeks if you're looking at, growth or certain aspect, all the way through, pollination and all those things could take months. And so it really depends on what part and what stage in the process you're really interested to look at the results of those plant microbial interactions. And again, that just comes down to the project. So it becomes very project specific on those things. And it's worth a discussion probably outside of this forum to try to better answer and make use of that. But as a general answer, the measurement itself, the IR measurement takes the order of minutes, but usually it takes, like I say, days to months to get the samples ready to go for these kinds of experiments.
Sampling time also related to our purpose?
Yeah, like I said, sampling. Sorry, what do you mean by sampling time?
To take the sample that that we can observe the communication between microbes and plants.
Yeah, I mean, that's going to be very dependent on the microbe and the plant and what the interactions in that environment are, right?
Okay, thank you.
Okay, well, let's thank the speaker again. I think we've gone through all the questions. If anyone has a burning question that they want to unmute themselves and ask real quick, I don't want to go over any questions, miss anybody, but I think I have gotten all the ones in the chat, and I don't
there is one question from Mohammed about the requirement sample size
go
for
ahead.
Animal tissue.
In the chat?
Yeah.
Okay, go ahead, Mohammed. If you're here, you can unmute yourself and ask, or Lucia, if you can read it. Here. What is the best practices? Oh yeah, okay, I see it. Yep. Mohammed, if you're here, you can unmute yourself and ask the question, or I can just read it here. Okay, that's not hearing you. It says, what are the best practices for samples, requirement sample size, especially with animal tissues and microorganisms for imaging purposes?
So, yeah, I mean, if you're dealing with animal tissues and microorganisms that need to be basically deceased in order to take the measurement, you want to limit the number of samples as best as possible to get at least reasonable statistics on what you're trying to measure. And so I could use the case in a lot of our mice studies that are being done. Most of our researchers are just working in triplicate. And so again, it's just comes down to keeping the number of mice down to as low as possible, while still trying to get statistical meaningful information out of it. Again, this is going to vary depending on the ethics involved in what animal and what you're looking at, because those, again, will differ and be different depending where you are. In terms of sample size, the mouse brain, to give you an idea, is basically 1 square centimeter by 7 microns thick. And so that kind of is is kind of a size that we will look at. Other tissues we've looked at are intestines from pigs. Again, you're looking at very small kind of sections of that. But those are kinds of the things that we need to look at. The requirements are that the material be thin enough, but yet thick enough. So what I mean by that is it needs to be thin enough to allow IR light to go through, particularly in transmission mode, which is where we do the best imaging. But also thick enough that there's enough material there to take the measurement. And so with biological samples, we're finding a happy medium anywhere between 7 and 15 microns, kind of as a thickness range. But again, it becomes very tissue specific, and it requires some experimentation to determine what that will look like. But yeah, that's kind of what we see here. And so when we're starting a new project with any sort of tissue like this in mind, we will ask for the extremes, right? So we'll ask for a control and ask for something that is, far along in the whatever the perturbated state is going to be, whether it be a disease associated with it or a lengthened drought tolerance, kind of whatever that kind of max perturbation state is, to see if we could determine, how or what changes we expect in between, as well as to determine the thicknesses of these things and that kind of thing. So hopefully that kind of answers your question.
Okay, so why don't we just cut it off there? There is one last question about are there opportunities to complete postgraduate studies through research projects, either at the Canadian Light Source or the university? I'm sure there are.
Yeah, that's best to reach out to various university professors that operate these programs. They're the ones that are going to be able to provide the best support in terms of completing those kind of research projects. Where we at the Canadian Light Source offer, measurement techniques and the ability to take those measurements, but it's a lot of work by our research PIs that come to the facility that do those work. And so if you're looking for those postgraduate study opportunities, I would look to those researchers that are already doing work at synchrotrons, and you could find them by looking at our publication lists of those kinds of things.
Okay, fantastic. Well, thank you for giving us your talk today.
Yeah, no, it was a pleasure.
Thank the Canadian Light Source, Lucia, as well, to helping us get this series off the ground of the application of synchrotron light sources to agricultural and context. So this is the first lecture in that series, and stay tuned for more of them. Thank you, everyone, for coming today. All right, I'm going to stop the recording.